Okay, we are going to have a talk given by Professor Clark Glymour. Clark is a university professor of Carnegie Mellon University. He's also a member of the American Academy of Arts and Sciences. Basically, in the 1980s, he, together with his student, Peter Sbertis and Richard Shines, created the field of causal discovery. And they developed the PC algorithm, Peter Clark algorithm, and a lot of other algorithms that are still the most popular method in causal discovery. And right now, a lot of well-known names in the field of causal discovery were just students, his students or students of his students, including Gigi Zhang here, who was a student of Peter Sbertis. So let me see. Okay, it's on mute. So today, Clark will talk about two dogmas of methodology. Actually, this talk is not just, it's not really technical, but it's not purely philosophical. Essentially, it's about the mindset regarding how we can develop innovative new scientific methods. Clark, are you ready?
I don't know. Can you see my screen?
Not
Cohen?
yet. Oh yeah, okay. I have a. Let me do this. I think I have a set of slides. If needed, I can share the slides. I can see you now.
Okay.
Share screen. Can you share a screen? Otherwise, I will share my screen.
I'm hitting multiple participants can share the screen. So it says,
you are using the same set of, you sent me the slides, you are using the same, right? You didn't change the slides. Okay, good. Let me share my screen.
okay, do you want to move the slides and I'll talk through them?
Yes. Okay, I'm ready.
All right, good. So despite the title, I'm going to talk about several methodological issues, and I will talk about them more as a philosopher than as anything else. And you know what philosophy is, it's destructive testing. So please go ahead to the next slide. So what I'm saying will be old hat to some of you, hence the cartoon for the English trope, carrying coals to Newcastle. Newcastle is where they mined a lot of coal. For some of you, it will be annoying, and that's really my audience. So there are a litany of objections to automated causal search from observational data. And they have produced a number of arguments. I think these arguments turn on dubious or false claims or objections that, if you fairly applied them to conventional statistics, would be as forceful. So altogether, I'll call these objections shibboleths. And what I'm going to do is review some of them. Go ahead, Kuhn. So I've got 7 of them. One is that Hume proved that there's no such thing as causation. Another is that causation is only evidenced by controlled experiments. Third, experimental outcomes should be pre-specified. Observational studies provide suggestions, not evidence. Computerized scientific discovery is impossible. Multiple hypothesis tests must be corrected for. And automated search assumes faithfulness or frugality or some such simplicity principle. Please go ahead, Kuhn. So first one, Hume showed that there's no such thing as causality, and anyway it can't be defined. Well, Hume did no such thing, and he didn't even think that it is the case that there are no causes in nature, and the claims that he does reveals what I call the fundamental theorem of history, which is that nobody reads, at least when they're citing philosophers. Now, it's true that cause has been defined in lots of ways, and there is no agreement in definitions, but by parallel reasoning, the same is true of probability. It's been defined in lots of ways, including by Hume, but not in a way that has produced agreement. Go ahead, Kuhn. So let's take the proposition that only controlled experiments can reveal causal relationships. So this is Fisher, who is famous for this view, but actually he was back and forth about it. And next slide, please. Because it's sort of ironic. Fisher did postgraduate work in physics and astronomy. He then went to work at a biological research station and worked on the development of evolutionary population dynamics. And the fundamentals of astronomy and evolution were established almost completely without directly relevant experimental evidence. And that applies to a whole range of things. Kepler's laws, Newtonian gravitation, general relativity, evolution by natural selection. The closest thing you can find to an experiment in Darwin's work is dropping seeds into the ocean and seeing where they float. So another common complaint is that observational investigations only provide suggestions, not evidence. And up to my right, I have a distinguished statistician whom you may recognize, who said this to me many times, but so have many other statisticians. Well, I want to draw a contrast. Here are some suggestions. Drinking bleach will cure COVID-19. There's no intelligent life on Mars. There is intelligent life on Mars. There's intelligent life somewhere else in the galaxy. We live in a computer simulation. Those are just guesses. Claims with evidence, which were obtained entirely by observation, Kepler's laws, Darwinian natural selection, and Cannizzaro's chart of atomic weights. I have a picture here of Stanislav Cannizzaro because he is, to my knowledge, the first scientist to ever discover something fundamental by a search algorithm. Okay, Kuhn, next. So another claim, which is now standard in the methodological literature on experiment and ipso facto applies to observational data, is that the outcomes should all be pre-specified. Now, that is a slogan we honor in the breach and which we are morally required to honor in the breach, because any experiment can have surprising, untoward, unwelcome outcomes that couldn't have been pre-specified. The experimenter didn't expect them, didn't know about them. And when an experimenter finds them, he is obliged to report them. And furthermore, the experimenter is obliged to look for them. Next slide. Good, next slide. So, no, one before that, you skipped one. So, there have been arguments that automated causal discovery is impossible. One argument put forward by a famous philosopher of science, now dead, Carl Hempel, was that real scientific explanation must involve unobserved causes, and no computer could find unobserved causes. But we know that's just false. It's an instance of the standard kind of argument, I can't think of a way to do something, therefore necessarily it's impossible. I think the first refutation was Peter Sprudy's fast causal inference algorithm, but there have been many other methods for asymptotically correct inference to structures with unobserved common causes. Furthermore, a related objection is that samples may be from mixed causal structures. But even in that case, Kuhn and Glymour, not me, but another Glymour, have shown that in fact, the structures of the contributing samples, if they are sufficiently different, can be recovered from the mixed data. That's not to say that there isn't a lot of work to do, there's a lot of stuff we don't know how to do. We don't, for example, know how to build a unified theory. I give thermodynamics as an example, but you can think of many others from disparate, fragmentary regularities. Go ahead, next, Kuhn. So multiple hypothesis tests must be corrected for, and there's a kind of argument for that. The argument is a version of what is known in philosophy as the preface paradox. So here's the preface paradox. I believe every sentence written in Causation, Prediction, and Search, but I also believe at least one sentence in that book is false. And that's probably a true claim, true of me. The multiple hypothesis testing paradox, which you all know, I'm sure, is that if a null hypothesis has been rejected at some level, but a whole bunch of tests have been run, the probability that at least one null hypothesis was falsely rejected is greater than whatever the rejection level was for the individual tests. And a similar argument could be applied to search algorithms that don't use hypothesis tests, but use scores, although I don't know of any proposed method for correcting multiple score comparison. Go ahead, Kuhn, next slide. So one of the things in evaluating an argument like this is to consider the utility of information and disinformation. If we search, we will make errors. Our precision will be less than perfect, but our recall may be substantial. If we don't search, our precision may be excellent, but there are a relatively small number of experiments that we can perform on a large data set. And on some data sets, there are no experiments we can perform. So our recall is essentially nothing. So that's the trade-off. And it's important to view the positive information side of search as well as the risks of error. Go ahead, Kuhn, next slide. So there are a variety of corrections for multiple tests. And I don't mean to suggest that correction for multiple tests is always wrong, but I want to point out a feature of all multiple correction methods, multiple test correction methods I know of, which is troubling. All of them require a set or a list of tests to be corrected. And the decisions about what tests to retain or what decisions to retain depend on the set selected or the list. And they can vary dramatically as that set is changed in particular, or that list is changed in particular, as new tests are added or considered. So what is the appropriate set of tests one should use in correction? So should I use all the tests used in eliminating a particular edge in the PC algorithm? All the comparisons made in adding an edge in the greedy equivalence search algorithm? All tests or comparisons made in the entire search? All the tests or comparisons made in any search in the course of a project? All those that have ever been published, ever. Now, you may very well have views about what the right choice is, but I don't know a warrant for the right choice, which has to do with properly correcting errors. Kuhn, go ahead. Search assumes some simplicity criterion, either faithfulness, which says every independence relation manifested in the data is a consequence of the causal structure in the true directed graph. Frugality says the true graph is the DAG, considering only DAGs, with the fewest number of edges that satisfies a Markov condition for the probability distribution estimated from the sample. Now, it's not true that every search method makes one of these assumptions. In particular, ICA and related search methods don't assume faithfulness or frugality. And furthermore, instances of faithfulness are essential to experimental inference. If you infer that treatment is not a cause of an effect from their independence, conditional on whatever covariates, you're using an instance of faithfulness. But I should say informally, last year I attended a seminar in our statistics department on causal inference, in which students presented and analyzed the inference to a parameter in some causal model, otherwise fully specified. I never saw a single example in which the specified model violated faithfulness. I think it is, in fact, tacitly assumed all over the place. Please proceed. So my lecture is brief, and I will summarize it briefly. There are a litany of objections to automated search for causal relations that are false or unfounded or not even-handed. That is to say, they would apply as well to causal inferences from experiments. The real problems I see are that automated data-driven search is in fact insufficiently used for many reasons. One reason is the absence of up-to-date informative guides as to which of a plethora of algorithms to use in what sort of data settings with what sort of assumptions. And finally, the influence of the shibboleths, which I hope you will help to decay. And go ahead, last slide. My attempt at xie in Chinese script. Thank you very much.
Thanks a lot, Clark. So it's high level, and at the same time, I think basically you summarize those essential criticisms when we are trying to develop new science or new disciplines of science or new scientific methods. So now we have time. Actually, it's brief and very informative. Now let's see whether there are questions from the audience. If you have questions, you can directly send a message by chat, or you can just raise your hand. I think someone raised a hand at some point.
I have my chat up. I don't have anything in it.
Previously, I saw someone raise a hand. Okay, so let's wait. In the meanwhile, let me just start. So Clark, 35 or 7 years ago, you started thinking about, you started developing methods for causal discovery. And right at that moment, I guess probably just wanted to find a causal relation among the measured variables. In the long run, now given that that problem has been solved pretty well in a lot of situations, what do you think would be the situation of causal discovery in 5 or 10 years? Any idea?
Well, I can give you hopes, not predictions. First of all, I hope that methods will spread in their use. I mean, I see some very old algorithms, like the PC algorithm, are beginning to be used directly or indirectly. But, the PC algorithm is pretty old hat. And there have been wonderful developments, principally since 2005. And so far as I know, they're basically unknown to scientific practitioners who could make use of them. I would hope that search methods are used to search for covariates that need to be controlled in experimental studies, especially with human subjects. I think that randomized experiments without covariates have a rather limited guarantee of benefit unless the covariates are controlled for. Of course, we have the enduring problem of unmeasured covariates, but in fact, with some methods, sometimes we can identify unmeasured covariates. I hope that causal search will become more hierarchical so that latent variables of latent variables can be identified. I hope the distributional restrictions on those kinds of searches will be reduced and the variety of cases to which it can be applied will become wider. And yeah, those are my hopes. And if you prodded me, I could probably produce a few more, but those are the ones that come to mind from an unexpected question.
Yeah, great. To me, maybe that would be even the foundation of the next scientific revolution, in the sense that causality is not mysterious anymore, right? You can just use automated computational methods to discover and use causality.
I will say that the statistical attitude towards causality, though not towards search, has changed radically in my lifetime. I remember a now quite distinguished statistician who, when he was first hired—
Give you 1 second, please.
At Carnegie Mellon, came into my office, asked what I was working on. I said, I think about causality. And he said, well, I'm not happy with talk of causality, and left. But now his statistics department is all over the subject of causality. Times change, and I hope attitudes towards search will change as well.
Okay, now Gigi actually has a question. Gigi, go ahead.
Thank you. Clark, good to see you here, and thanks for the provocative talk as usual. So I have a question about your remark about score-based methods facing a problem of a multiple score comparison. Do you mean that?
That was just a statement of ignorance. There may be methods proposed for doing that. I just don't know of any.
Well, actually, I don't know. I'm just wondering, is that actually a problem specific to algorithms like GES? Because I'm thinking if you really just have, right, if your goal is to search for a structure with the optimal score, and suppose you do brute force exhaustive search, let's not worry about the feasibility for the moment. If your goal is really just to, based on a given data, find the best scoring structure, it seems I'm not sure whether there will be a multiple score comparison problem there, right? Because in the end, you just try to find the best score. Maybe GS is special because GS somehow, right, involves a lot of, I need to think about that, because in the end, it actually involves local score comparison. Rather than just compare. If you really just have a global scoring function and try to find the best one.
Well, there are various optimization algorithms that search for a global score and try to optimize it. And the issue is different for them than for a local search like the greedy equivalence search, where you are making multiple decisions about whether or not to introduce a particular edge.
Okay, so maybe maybe GES is quite special in this aspect among the score-based methods. And also very quickly, Clark, did you mean in the end that you actually attempted to write those 2 characters, 谢谢. You said you.
I copied them from
Oh, I see.
the
Okay.
web, of course.
I'm just wondering.
You think I'm foolish?
No. I was.
Okay.
You are
Sorry
trying.
to interrupt you because we got a question from the audience. By the way, Gigi, I want to add something to Clark's response to your question. So even for GS, even for any score-based method, you can still have something like a multiple testing problem. You know, you decompose the score into local scores, but you use the same penalty, the same way to penalize the different local scores. Actually, that's still, you can see a problem because depending on the correlations or dependency between the different variables, this part showing this treatment might not be optimal. So we can still have something like multiple testing problem. Yes, just want to give share a bit, bit more
thank
thoughts.
you. Yeah, so maybe the difference between local scoring and global scoring, I don't know, but we can talk about it later. Yeah.
Cool, thank you very much, Gigi. And Clark, here is another question from the audience, from JK. So yeah, could you ask, are those decks produced by score-based method real causal structures?
So here's what makes something a causal structure. The person who offers it says it is. That's what makes it a causal structure. And in saying so, is committed to the independence relations that result from ideal interventions on the variables according with the causal structure. That's what makes it a causal structure. Literally, it is the disposition of the advocate or presenter to treat it as such with the ensuing empirical commitments that go with that claim. A mathematical structure isn't anything in itself except a mathematical structure. Okay, that's all I have to say.
Yeah, wonderful. Thanks. Because of time constraints, we have to stop here. Thank you very much, Clark.